Good morning, everybody, and welcome to this lecture. We will continue our discussion on functions and then also look a little bit at trigonometry. But before that, I wish to do something which I had promised you last time, that is remind you of the proof of the harmonic series going to infinity. So the harmonic series is, just a second, uh, it is this one. And we had quite a lengthy discussion last time as to where this might be going. And most of you initially felt that this will go to something like 2 or 3, and some people said maybe at the most it will go to 3.5, or some people even claimed it might go to pi. Just because pi is an interesting number, you felt it might go to pi. And if you run this on a computer and you look at the first 10,000 cases, you will go nowhere beyond maybe 10 or 20 or 30 or something like that. You will never be able to see anything more than that. But then I told you that this actually goes to infinity, and let us refresh ourselves with the proof of the proof of this going to infinity. And I'd showed this in May of 2020, I think, in one of the first classes that we did after the training program. And I don't know how many of you were actually there, so it's okay to do it again. Now, the first thing we need to understand is this series, which you see ahead of you, is exactly greater, strictly greater than this series. Right? So then let's say we have 1 over 6, 1 over 7, 1 over 8, following 1 over 5. And let me put 1 over 8, 1 over 8, 1 over 8 4 times. And don't worry about that. We'll look at the first few terms. The reason I say it is greater is because we can compare every term with one another. So 1 is equal to 1. We can forget about that. Half is equal to half. 1/3 and 1/4. We definitely know that 1/3 is greater than 1/4. So we can say that this is greater. So as of now, the top sequence is greater than the bottom sequence. 1/4 is again the same. And then you have 1/5, 1/6, 1/7, and 1/8 in the top series. And in the bottom series, you have 1/8, 1/8, 1/8, 1/8. So again, we can definitely say that this is greater, because 1/5 is greater than 1/8, or 1/6 is greater than 1/8, 1/7 is greater than 1/8, and then 1/9 is equal to 1/8 is equal to 1/8, right? After that, what we could do is, when we cross 1/8, let's say we have reached till 1/8. Now in my harmonic series, I have 1/9, 1/10, all the way up to 1 over 16. And what I will do is I will just put 1 over 16 everywhere in my bottom series. So I'm playing around with two things here. The top one is the harmonic series, and the bottom one is a new series which I have created to prove to you that the harmonic series goes to infinity. Now, do you agree that the top series is bigger than the bottom series? Because 1 over 9 is bigger than 1 over 16, and all of these are bigger, and then this is equal. So that shouldn't matter. As long as it's greater than that, we are fine. So let us now decide upon one thing. Before I go into the proof, I wish to get some consensus on this. Do you all agree with me that if a series which is smaller than our harmonic series goes to infinity, then will that imply that the harmonic series also goes to infinity because it is greater than that? Will you all agree with me? So if I show to you that something smaller goes to infinity, then this one would also have to go to infinity. Now we have to be very careful when we play around with infinity. This is one of the biggest rules of mathematics, and a lot of proofs that you see in all these books and the internet and these puzzles involve playing around with infinity and zero in an illegal way, which is not allowed. You cannot divide by zero, you cannot divide by infinity, multiplied by infinity. You cannot do that without keeping some rules in your mind. Because I could say that 7 and 6 are same, because 7 times infinity and 6 times infinity is both infinity. That doesn't mean that 7 and 6 are the same. So when we use infinity and zero, we have to be very careful. But in this case, I'm doing something which is perfectly legal, because I'm saying that if something goes to infinity, anything larger than that should also go to infinity. That completely makes sense. Remember that the other way around might not work. If I have something that goes to infinity, something smaller than that need not go to infinity, right? It need not, because we don't know it is how small. Because just because something goes to infinity doesn't mean everything nearby also goes to infinity. You have to be very careful as to how small it is. But here we are safe, because I wish to show that the bottom series goes to infinity. The question we want to try is to prove that the harmonic series, which is the top series, goes to infinity. But I feel it's a lot easier to show that the bottom series goes to infinity. And since the harmonic series is bigger than our bottom series, we are done if we show that the bottom series goes to infinity. So now let us show that the bottom series goes to infinity. What was it? It was 1 plus half, and then I had 1/4 plus 1/4, and then I had 1/8 plus 1/8 plus 1/8 plus 1/8, right? And then I had 1/16 8 times. Let me just put times 8 over here. And then we will have 1 over 32, and we will have that 16 times, right? We'll just keep doing this. Then we'll have 1 over 64, which we will have 32 times. And then we'll have 1 over 128, 1 over 128, 64 times. And we'll keep doing this. This one goes to infinity, and it's very easy to show because 1 plus half is half. If I put the two 1/4ths together, I get half again. So I'm adding one more half to my sum. If I put all the 1/8ths together, I will get one more half because we are adding 4 1/8ths. So 1/8 plus 1/8 plus 1/8 plus 1/8 is half. So I will group them together and I will add it to my sum. So I got one more half. The 1/16th 8 times also gives you half, correct? So I can group all of that together. I get one more half and I put that into my equation. The 1 by 32, which is happening now 16 times, if you add all of those together, that is 16 by 32, which is again half. So basically, every time I take these groups of numbers, I get half. And how many such groups are there in my sequence? As many as I want. I have infinite such groups. The groups get larger and larger, true, but every time it's a finite number. When I talk about 1 over 64, I have 32 such numbers. I can add all of them together, I get half. 1 over 128, I'll have 64 numbers. I add all of them together, I get half. So basically, this goes to infinity. It's easy to show. Remember what I told you last time. How do you show that a series goes to infinity? You have to show that it will cross any number that you want. Only then it goes to infinity. Because if it can cross any number, any possible finite real number, the only possible answer is this guy goes to infinity because he's able to cross everything. So think about this. It's like you're traveling on a road. Now you want to show that this road will take you to infinity. Now, how would you show that? You'll show that any distance that you require, this road will travel that. So if I want to travel 100 miles, this road will go 100 miles. If I want to go 1 light year, this road will go 1 light year. If this has to go trillion light years, it will go trillion light years. So basically, any distance, if it's going, then the only possibility is that it goes all the way to infinity. Because if it was not going to infinity, then we could find a number which was greater than this, to which the road would not go, right? Because if it's a finite number, you can add 1 to it and get another number which is greater than that. So that way, this series can go to any number that you want. If you want it to go till 10, just pick those sets of halves. If you have to pick 20 different halves, right? Half plus half plus half, you should do it 20 times, you'll get 10. So we pick 10 groups. So basically, we have to pick groups of 2 to the powers, all of these powers, we have to group them together and we have to make 10 such groups because each group will add up to half. I mean 20 such groups. Each group will add up to half. If I add all those groups together, the 20 halves together, I get 10. Yeah, somebody's saying 19, which is actually correct because I'm having one already at the start. So I just need 19 more groups, but you get the idea, right? So we can basically take as many groups as we want and we can reach wherever we want. So it will take you a lot of time though, because you can think about it, right? To reach 20, we would need 39 groups other than the one. So basically 40 groups. So you have to go all the way till 2 to the power 39. And then that term will occur 2 to the power 38 number of times. So you'll have 1 over 2 to the 39, 1 over 2 to the 39. It's a lot. But we are not bothered about how long it takes. As long as there's a way to do it, we are done. So this goes to infinity. And the harmonic series is bigger than this because every term of the harmonic series was either equal to this or bigger than this at every point. So the sum of that has to also be bigger than this, which means that also goes to infinity. So it's very strange that we have two sequences, two series. One of them is greater than the other, but they all go to infinity. So that's the beauty of infinity, because I could have this series here, 1 plus 1 plus 1 plus 1, all the way, it goes to infinity. And I could also have 10 plus 10 plus 10 plus 10. It also goes to infinity, but at every point of time, this is 10 times this much. That doesn't really matter. Both of them go to infinity. So when I was a kid, I had this joke that I told my dad. I told him, Dad, if you run at 10 kilometers per hour and if I run at 15 kilometers per hour, I might be faster than you, but we will reach infinity at the same time. The time taken for us to reach infinity is the same, because both of us will take infinite seconds to reach there, irrespective of how fast we run. So even for light to reach infinity and for an ant to reach infinity, it's the same amount of time. So that's how you think about infinity. It's not a number, it's a concept, and you have to be very careful when you deal with it. But in this case, we are fine. We did not do anything in this case which was illegal, so to speak. And by the way, when I say illegal, I don't technically mean it's not allowed, because very famous mathematicians like Euler, Ramanujan, and all these people have played with infinity. That's why Ramanujan was actually called the man who knew infinity. But they did it in legal ways. They played around with it, but it still made sense in some sense. For example, Ramanujan played around with infinity in a different plane altogether. He brought in complex numbers. He changed the whole dimension of what we are working around with, and that's how he was also able to show that 1 plus 2 plus whatever adds up to minus 1 over 12, such things, right? So those are borderline legal. It's a gray area. Some people will say that's allowed. Some people will say it's not allowed. It all depends. It's like in America or in India. In some states, it's legal to marry at the age of 18. Some states, it's legal to marry at the age of 16 or 21, right? It depends where you are. So similarly here, it depends in which plane you're playing around with. If it's the complex number plane, the rules change. If it's the real number plane, rules change. If it's natural numbers, rules change. Okay. So now that that is settled, we know that the harmonic series diverges. We still didn't prove that this thing diverges, where it's the sum of all reciprocals of primes. But I told you that this is a slightly harder thing to show as it goes into logarithms and it uses a little bit of calculus. We don't have to worry about that. It's believable, I feel, because there are so many primes. You can kind of believe that adding up all their inverses should go to as big a number as you want. Okay. So now talking about our favorite topic, the functions that we were discussing. So we defined injective functions, which are one-to-one, but I'm hoping now that you will be free to use this slightly more complicated word. Rather than just saying one-to-one, we can say injective. Then there was the onto function, which we called surjective, right? Surjective, not subjective, surjective. So this is one-to-one, this is onto, and if both of them work, we call them bijective. And we didn't actually see examples of it. I gave you examples in terms of diagrams. We drew a set, we drew another set, we kind of joined dots, and then we said, okay, this might be injective, bijective, but we didn't actually see concrete examples. Now, let us actually look at a very interesting function, which we should, by looking at it, we have to decide whether it is injective, bijective, surjective, whatever. The first rule, whenever we talk about functions, you might recollect from last week, we have to define our domain and our codomain, D and CD, and we have to say where this place is where we are working. It's very important because functions are very abstract. Numbers themselves are abstract, right? So how do you define the number 3 or how do you define the number 10, right? You don't really see the number in nature. You just see examples of the number. Now I might say I have 1 water bottle, but that doesn't really explain what is 1. It's a quantity. So math in general is very abstract, and we have to be very careful when we define where this whole event is happening, whether it's happening, in the real numbers, whether it's happening in the natural numbers, because some things will not make sense if you define them in the wrong place. It's like you want to wear gloves, but you need to state where you're going. If you're going to a cold place, it makes sense. But if you're in the summer of New Delhi, there's no need to wear gloves. It doesn't make sense. So sometimes you have to be very careful when you specify where this is happening. So that's the domain and the codomain. So let's be very safe here. Let's define the codomain and the domain both to be real numbers, because when we deal with real numbers, we have everything at our disposal. We have all the positives, all the negatives. We have 0, we have rationals, irrationals, we have pi, we have e. We are good. The only thing which we don't have here is square root of -1 and those guys, but we don't have to worry about them now or at any point of time. I think in any of my lectures, unless people request me to talk about it, it's not a very it's not a very easy thing to explain, because I don't think I myself understand it so well now. And it's something that many people find it hard to understand after a lot of years in mathematics as well, because you never really can make sense of negative square roots of negative numbers in the complex plane. It's very abstract. But let's stick with real numbers now. We'll define a very nice function. Let us say that for every number in our domain, we will do the reciprocal of the number in the codomain, and we will stick with the theme of the harmonic series. So we define f of x to be equal to 1 over x. So you take a number, you do its reciprocal, and we have to see whether the answer will be in the codomain. It looks like it, because I don't think you can do a 1 over a real number and end up with an imaginary number. It doesn't make sense. The first question I want to ask you is, does this playground look good, or do you see some things that stare at you which do not make sense? I'll wait for I'm already getting answers here, but I'll wait for other people also to spot it. There's something really weird going on here. We have defined our playground very well, but we need to make a slight correction to our rule when we define this function. Very good, very good. So 3 people have gotten it. I'll just wait for 10 more seconds to see if somebody else will also get it. Where I'm defining a function f of x to be equal to 1 over x. Is there anybody else who can notice something? Okay, good. The problem is with 0. 0 is a real number, and this function doesn't look like it's well defined when x is equal to 0. Remember, when we say what is a domain, that function should be defined at every single term in our domain. So everybody has to have a partner. You cannot have a number in our domain who doesn't have a partner in the codomain. Everybody should be matched with somebody. And this has nothing to do with one-to-one. This has nothing to do with onto or bijective. It is a rule of functions. Now, on the other side, on the codomain side, there might be people who are left alone. There might be people who are having 2 partners in the domain. That's totally fine. But from the domain, everybody should have only 1 partner and exactly 1 partner. That is the rule. You cannot match 1 person with 2 people, and there cannot be somebody left alone. So 0 is part of our domain, and he doesn't have any partners in the codomain because we cannot do 1 over 0. It's not a well-defined operation. So we will just do r minus 0. So now we are safe. Remember that notation there is because we are dealing in sets. So real number is a set. So from the set, I'm removing an element, because I cannot just do r minus 0 without the brackets. That doesn't make sense, because then I'm subtracting a number from a set. You can only subtract things which are similar, right? So I'm subtracting now a set from a set. So now we might be in a better position to understand this. But let's just see if there's any other exception. Is there any other real number which, if I do 1 over that, I will not find an answer in my codomain? Is there anything? Let me just draw a divider here. So this side we have somebody saying pi or e. Why is there a problem with pi or e? You can do 1 over pi. That's still a well-defined irrational number. You can do 1 over e. That's also a well-defined irrational number. They'll all fall in the codomain. Pi will be matched to 1 over pi. E will be matched to 1 over e. 1 over pi will be matched to pi. 1 over e will be matched to e. So, okay, those guys are not exceptions. Any other problems, guys? Negative numbers, any problems? I don't think so, because reciprocal of a negative number stays a negative number, and you can match it to somebody on the other side. Both sides we have real numbers. Actually, on one side we don't have 0, but on this side we also have 0. So in our codomain we also have 0. Okay, so looks like there's no exception. So this is let's see if this function is well defined. Is there anybody in my domain who is being sent to 2 people? Because if that's happening, then it's a problem. You can only match 1 person with 1 person. Am I having anybody in my domain who is having 2 different partners in the codomain? Is there any number which, if I do 1 over that number, it gives me 2 different answers? No. Okay. What about the number 1? The number 1 will be matched to 1. So that's okay. Is there? Yep. So there's no exception. Okay. So function is well defined and we are good to go. So we defined it. We looked at the exceptional case. We got rid of that. And we checked if the definition works. We see if everybody has a partner. Everybody has 1 partner. Now we can start our investigation. Let us check if this is 1-to-1. That's injective. How did we define injective? We defined it in a nice mathematical way. We said that if 2 people are being matched to the same person, then both those people have to be the same person. That's what we defined as the meaning of injection. We said the only way by which 2 different people can be matched to the same person is if both of those people are actually the one person. So there is no way by which two unique people can be matched to the same person in terms of injectivity. If the function has to be one-to-one or injective, one person should be matched to one person and no one else should be matched to that person. So let us check if that holds true here. Now we have to focus on our codomain. We have to focus on our codomain and we have to check if there is any number in the codomain which is the solution to two different numbers from our domain. Let's think about this. What about the number -1 in the codomain? Which number from the domain brings you to -1 in the codomain? -1, very good, because 1 over -1 is -1. Is there any other number that will bring us to -1? No. Let us actually check this mathematically. Let's not rely on examples because we cannot verify for infinite numbers, right? I might check for 1, -1, 0, or 0 is not there, or pi or e, but there is no human way to check for every possible real number. It will take us more than the entire age of the universe. So we have to do this smartly, and we should not use any example because only then we can be assured that this will work. So let us use our good old friend, the proof by contradiction. So let us start our proof by saying, okay, let us assume that two people exist. Let's call them X and Y, and let us assume that both of them are matched to the same person. If this happens, the function is not one-to-one. But we are now hoping to imagine this, and we will hope that we will find some mistake in our assumption, which will then tell us that there is no way by which two people can be matched to the same person, which then concludes our proof that one person is matched to one person and no one else is matched to that person. This is called proof by contradiction. So suppose I want to prove that, let's say there are only two possibilities. Let's say that I can either be 10 years old or I can be 20 years old. Those are the only two possibilities. Okay, imagine. So then I will say that, okay, let me imagine that I'm 20 years old. And then somebody proves to me that I'm wrong, then it means I'm 10 years old. That's the logic here. This logic will only work if there are only two possibilities. If there are 5 or 6 different possibilities, then you cannot use this. Because just because one thing doesn't work, it doesn't mean which of the other 4 is the correct answer, right? This will work when there are only two values possible, true and false. So here we have only two possibilities. One is the function is injective, one is it's not injective. So we will assume that it is not injective and hope to show that it's not injective, which means it has to be injective. Okay, so we have two people X and Y, and we are assuming that f of X equals f of Y. Basically, we're assuming both of them are matched to the same person. So then in that case, we are saying that 1 over X should be equal to 1 over Y. Right? We are saying 1 over X should be 1 over Y. It goes to the numerator. And if I take Y to the left-hand side, it also goes to the numerator. This implies that Y equals X. Because Y came here, X came there. Did you quite follow what happened over there? Does anybody have any confusion as to how this proof went? Oh, there were 3 steps. First, we defined X and Y. Okay, good. So we showed that Y is equal to X. What does that mean? If two people are going to the same thing, they have to be the same person. So this function is actually injective. Let me repeat this very quickly for some of you who might not have gotten that last part. We started by assuming that there are two people, X and Y, in our domain who are matched to the same person in our codomain. Okay. If that actually happens, then our function is not injective. So we said if there are two people X and Y, then we are assuming that f of X and f of Y are the same thing, which means 1 over X should be the same as 1 over Y, because remember our function is defined as taking the reciprocal of the number. So f of X is 1 over X and f of Y is 1 over Y. So okay, if 1 over X is 1 over Y, what does that mean? It means that Y is equal to X, because if 1 over X is equal to 1 over Y, you can bring Y to the numerator on the left hand side. You can bring X to the numerator on the right hand side. So basically on the left hand side you have Y, and on the right hand side you have X. So then Y is equal to X, which then implies that they were not two different people, they're actually the same person. If anybody has any question, just you can unmute your microphone and ask me. You don't have to feel shy about it. This is something it's not so easy to follow. It's a little tricky because you're assuming something wrong and then you're realizing that you are wrong about that assumption. It's very stupid logic, right? Why would you even have to assume something which is wrong and then realize that you are wrong? Why can't you just start off by assuming that you're right? Because if you start off by imagining that you're right, how do you prove that you're right? How do you actually show that something is correct? But if you imagine something which is wrong, and then you show that what you imagined was also wrong, then you can show that you are right. That's basically the logic. I start off by thinking it is injective. I realize it's not injective. I mean, I start off by thinking it is not injective. Then I realize that my assumption was wrong, which means that it has to be injective. Okay, so we are good now. This function is one-to-one, well defined. Now let us check if it is onto. So onto means every person in the codomain should actually be somebody's partner from the domain. Somebody quickly said it's not onto. Ruhi, can you tell me why it's not onto? Very good. I'm getting beautiful answers here in the chat. Let's see. So Ruhi was the first person who said it's not onto. Do you have? Perfect. Wonderful. 0 has no partner. Because remember, 0 was not part of our not part of our domain, but it was still a part of our codomain. We had defined the function to the real numbers. So 0 exists in our target group, but nobody has been sent to 0, because you cannot do 1 over something to get 0. How do you do that to a real number? Which is the real number, which if I do 1 over that, I get 0. It's not possible. I cannot do 1 over any number and get 0. I might get very small numbers, because 1 over trillion might be very small, but it'll never be 0. Unless you do 1 over infinity. But I know some people are thinking about it, but it's not something we can define easily. Infinity is a symbol, 1 is a number. You can define 1 over infinity to be 0, but then infinity is not a real number, so infinity is not part of our domain, so we're not having it in our target group to send to 0, right? So there's nobody who is being sent to 0. So 0 is left alone. So we have this set here, and we have this set here. This set is real numbers minus 0. Okay, this is real numbers. Sorry about the bad handwriting. From here we are sending people everywhere. We are doing 1 over 2, 1 over 3, 1 over minus 1, 1 over pi. All sorts of things are going on. But there's 0 over here. Nobody is being sent to 0. So this function cannot be onto. Remember, even if every single value in our codomain has a partner, but one guy doesn't have a partner, the function is not onto. Does anybody have any suggestion as to how to make this onto? Can we make this function onto somehow? Can we make sure that everybody in the codomain also has a partner? Wonderful. People are saying remove 0 from codomain. We removed it once from domain, poor fellow, because we said we cannot divide anything by 0. So he said, okay, fine, I'll go away from here, but at least I will sit peacefully in the codomain because no division is happening over there. But now we say that, okay, no one can even reach you by division, so we'll throw you out from here as well. That's actually a very good idea. We can get rid of 0 and make this also real numbers minus 0. And now we are set. It looks like we're onto, because now any number in my codomain, I know which is the number in the domain that brings me to it, because I can just do the reciprocal of that number. Remember, the reciprocal of a reciprocal is the same number, right? So if you want to go, let me use a red color. So we use red color to go from here to here. Okay, if you want to come back, you just have to do the same thing again. You just have to do reciprocal again. Because if I went from pi to 1 over pi, I can again do 1 over pi and come back to pi. Correct? Does that make sense? So everybody in the codomain, we can quickly find who is the person who is coming there by just doing their reciprocal. So basically everybody is being sent to their reciprocal, both ways. Everybody from the domain is sent to the reciprocal in the codomain. Everybody from the codomain is being sent to the reciprocal in the domain. Is being brought to them by the reciprocal in the domain. Good. It's bijective now. It is one-to-one and it is surjective. Everybody has a partner. Everybody has only one partner. Everybody in the codomain has only one partner in the domain. There's nobody left alone. It's a beautiful bijective function. We've defined it perfectly. So there is a one-to-one correspondence. Everybody is being sent to a unique everybody else. And now we can conclude one more thing when this happens. This is the last property of a bijective function. This is very, very important. This is the reason why these functions are used in mathematics in general. You might wonder, why do we even define all of this? The most important reason is this. If a function is bijective, it has to be bijective, okay? Not one-to-one, not onto, it has to be bijective. Then it means that the number of elements over here is equal to the number of elements over here. It's very, very important. In this case, both of them might be infinity, but that doesn't matter to us. As long as there's a bijection between those two sets, the domain and the codomain, we conclude that both of them should have the exact same number of elements. And this is very easy to show, because if one of them had extra elements, then it would not be one-to-one or it would not be onto, depending on which side has more elements, right? Does that make sense? Because if the codomain had more elements, then it cannot be onto. If the domain had more elements, it cannot be one-to-one. So if they have equal elements, if they are bijective, then they have equal elements. And this matters so much that I can actually even use this to show that there are more real numbers than natural numbers, because both of them might be infinity. So this is where functions play such an important role. They even allow us to understand infinity, because in this case we showed that both those infinities are equal to one another, the one on the left side and the one on the right side. But we can also use these ideas to show that one infinity might not be the same as another infinity. We can show that the natural numbers count infinity is very, very small compared to the real number count infinity. We can show that the even numbers, the total even numbers count is exactly the same as the total natural numbers count. Some of you might think that natural numbers should be 2 times more because there are odd numbers, but no, they're equal. You can use this to show that the number of prime numbers is exactly the same as the number of total natural numbers. Can you believe that you can actually show that the number of prime numbers is the same as the total number of numbers? You can also use this to show that the number of even positive numbers is the same as the total number of integers. You can use to show that the positive plus negative integers combined is the same as the total number of even positive numbers. I'll tell you what, you can also use this to show that the number of multiples of 100 is the same as the number of multiples of 1. How amazing, right? You can use this to show that the number of multiples of 100 is the same as number of multiples of 1. That's why it gets really tricky. Infinity is so strange. But remember what I told you, the real number count is more than the natural number count. So the real numbers come under a bigger infinity as compared to the natural number count. That's why the real numbers are called an uncountable infinity, and the natural numbers are called a countable infinity. And that I will leave as an exercise for you to think about. I will get into that next time. I actually wanted to start off trigonometry, but I think it will be a little too much if we do it in this session, because we actually covered something very important here. And so I will show you why the real number count is more than the natural number count. I'll also show you why the number of prime numbers is the same as the total number of numbers, why the number of even numbers is the same as the number of natural numbers. Remember, you can also show that the number of rational numbers is the same as the number of natural numbers. It's unbelievable, but it's actually true. You can show that the number of fractions, right, of integers like rational numbers, you can show that that count is also equal to the natural number count, but it's lower than the real number count. So real numbers are more than rational numbers. Even if you add all the real numbers, so even if you add all the rational numbers and all the negative numbers and all the positive numbers, it will still be very, very small compared to the total real numbers. You can also show that there are more real numbers between 1 and 2 than there are total number of natural numbers in the universe. So the number of natural numbers from 1 to infinity is smaller than the number of real numbers between 1 and 2. Why 1 and 2? I can also show you that the number of real numbers between 1 and 1.000000001 is still more than the total number of natural numbers. It's so interesting. And all of this can be done using functions. I'll give you a small hint for those of you who want to do this on your own. you have to try to construct a bijection between those two sets. If you are able to do so, then their count is the same. If you are not able to do so, then it means one of them is more than the other. You have to keep one as the domain, one as the codomain, define a well-defined function, and see if you can form a bijection. You should have something which is one-to-one and something which is onto. If that happens, then you can say that both of those sets, my domain and my codomain, have the same number of numbers. Okay, so I will now stop recording. If anybody has any questions, you are free to ask me. I will stay back for some time, but I just want to stop recording.